my favorite phrasing of that, what I feel about Gaia Data Release 2 is, it is fabulous, it is far from perfect, but it's even much farther from anything that has been available before. With almost 1.7 billion objects in total, and with over 1.3 billion objects having positions, proper motions, and parallaxes measured and published, and also with colors and photometry, it is a vast data set. It is a vast treasure trove for practically every field of astronomy. And the astronomers, as always in science, don't take any of these very precise numbers as granted. Always, in addition to the numbers given for each star, consider the uncertainties that are also given in the catalog, that these uncertainties are really telling about the precision of the data given, the astrometric data in particular. You can, for instance, read from figure 8 of the Data Reduction 2 paper on the astrometry of the Data Reduction 2. It shows a histogram, a logarithmic histogram of the measured parallaxes for about 1 million quasars. Since all the quasars, in fact, have practically 0 parallaxes, what you see here is not just the distribution of the measured values, but it is actually the distribution of the errors of the measurements. And these errors in this plot are normalized by the indicated uncertainty of them in the catalog. The red curve is the expected distribution of such measurements if it were a Gaussian, just 8% wider than what is given in the catalog. And the step curve is the actual distribution of the 1 million quasar parallaxes. As you can see, this very nicely fits together. So our uncertainty estimates are, except for this 8% underestimate, very realistic, and the actual error distribution is quite nice, namely roughly Gaussian to the first 3 orders of magnitude. Only at the very bottom, at below 0.1% of the quasars, you see that the curve deviates a bit to the up. There is a kind of tail of a bit larger errors than expected, a tail of less than 0.1% of outliers in the measurement of the quasars. Now, this is for the quasars, which are mostly faint. Their formal uncertainties is not very large, and the formal uncertainties depend on the magnitude of the stars. So if you look at figure B2 of the same paper, there you see the distribution of the estimated formal uncertainties of essentially all the stars in the Gaia Data Release 2. Let's concentrate on the middle of the 3 panels. Here you see the distribution of the estimated formal uncertainties of the parallaxes as function of G magnitude. The brightest stars are at the left, and the faintest stars in the catalog are at the right in this diagram. The 3 lines that you see are the median for a given magnitude, the 90th percentile at the top, and the 10th percentile at the bottom of the 3 curves. So what you see is that for stars fainter than 13th magnitude, the uncertainty increases with faintness of the stars. That is what you expect from just photon statistics. And at the faint end, most of the quasars that I have shown you are between 17th and 20th magnitude. At the faint end, we have seen that these formal errors very nicely coincide with the actual errors. What you also see is that the vast majority of the stars, more than 90%, look at the upper blue curve, have a fairly well-defined run of the formal uncertainties with magnitude, but there is a large field of uncertainty values above this line, large in extent on the plot, but small in number of objects. It's of the order of 1 or a few percent. These are the stars that happened to have bad luck in the measurement process, had been hit by the field of view of Gaia, especially rarely, so they have few measurements, or that they have had other bad luck in the measurement process. So the vast majority of them has a well-defined run, and this run of the uncertainty with magnitude has a clear cut at around 13th magnitude, and it's already leveling off between 13th and 15th magnitude, as you can see. This is where the uncertainty, the precision of the resulting astrometric parameters is no longer dominated by the photon statistics acquired in the 2 years of measurements, but by the residual calibration uncertainties in Gaia. It levels off at the level of 50 microarc seconds. That is a very, very small number, but that is representative for all the stars brighter than 13th magnitude. In addition to these formal uncertainties per source, users of the catalog should consider that they are not just random, uncorrelated errors of the individually measured parameters for individual stars, but in addition to that, there are systematic uncertainties for the whole set of stars, not just for an individual star. These are of several kinds, and they are described in the astrometry paper and also in the data release 2 validation paper. An example is the global offset of the parallaxes from their true value of the order of 20 microarc seconds to the negative. We know this from comparison of the data release 2 measurements with what we think are well-known external parallaxes, for instance. So, for instance, the quasars. We know all the quasars, we know in quotation marks, that all the quasars have 0 parallax. So if the mean or median parallax of all the quasars is minus 20 microarc seconds, we can assume that this is a systematic error of the parallax 0 point of data release 2. Now you may ask, why didn't we simply correct that? Well, we know it very precisely for the quasars. We know it also very precisely for a few others, sets of stars, for instance, the members of the Large Magellanic Cloud. The point is that this offset may be different for stars of maybe different colors. So the 0 point of the quasars may not be representative of the whole catalog. Quasars are faint, quasars are blue. It may be different for red stars far out in the halo of the galaxy. So every user should check himself whether it fits together, and check himself whether from the set of stars that he is treating, he could derive such a 0 point offset himself. Now, the same sort of stars have the same absolute luminosity, so their parallax on the average should go like the inverse square root of their apparent brightness. Taking a sample of them together, you can judge whether this is true or whether you better apply a small offset. Now let's look at figure 13 of the astrometry paper. The color code in this sky map shows the median parallax of the stars measured in small celestial patches, in very small pixels of this figure. This figure shows the area of the Large Magellanic Cloud. What we expect there is that practically all the stars, and thus the median of the parallaxes in each of these bins, is the parallax of the Large Magellanic Cloud, which is about 20 microarc seconds, which we know from other measurements outside Gaia. So first of all, the average of this is not 20 microarc seconds, but something near to 0. That is the expression of the 0 point error of the catalog that I already mentioned. But in addition, you see a clear pattern here. The characteristic scale of that pattern is 1 degree on the sky. And in these yellowish and bluish triangles, you see that the parallaxes of the measured LMC members, Large Magellanic Cloud stars, are predominantly positive in the yellowish triangles or predominantly negative in the bluish triangles. This means that on the scale of the order of a degree or less, we have systematic errors in the parallax measurements, correlated errors of the order of, again, 20, 30 microarc seconds. This is shown here in the Large Magellanic Cloud area because there you can easily show it. But this pattern is present on the whole sky. So this pattern and other systematic errors that are in the catalog limit the precision that you can get from averaging over the parameters of a set of stars, a number of stars, be it parallax, position, proper motion. Averaging of Gaia parameters at the very faint end gets an improvement in the precision over the precision of a single star, because there the individual errors are much bigger than these systematics, which are 30, 40 microarc seconds on the small scale, 20 microarc seconds on larger scales on the sky, and the 20 microarc seconds globally that I already mentioned. These are very small numbers, to be sure, but they may be disturbing if you look at stars brighter than 15th magnitude. It means that taking the average of, say, a dozen or 100 or 1,000 Gaia parallaxes of such stars, each have the precision of about 30, 40 microarc seconds, you will still be limited by these systematics. By averaging 100 stars, you will not get to a tenth of these 20 microarc seconds individual uncertainty. Generally, there may be special exceptions or clever uses of the data which can allow you to get further. For instance, differentially, one group of stars with respect to a different group of stars or so. But let's have a look at some beauties of the catalog. Look at figure C1, C.1 in the astrometry paper. Here you see three Hertzsprung-Russell diagrams created from Gaia measured parallaxes, Gaia measured magnitudes of sources, and Gaia measured colors. On the left, you see the Hertzsprung-Russell diagram of all sources in the Gaia release 2, which are nominally within 100 parsec, that is, having measured parallaxes larger than 10 parsecs, and having the parallax measured to a relative precision of at least 10%. What you see is a very nice main sequence, a very nice white dwarf sequence. At the bottom left, running diagonal, you see a nice giant branch and a nice red giant clump. Everything that you expect from such a diagram in the solar neighborhood. What you also see is a few percent of stars in this diagram not featuring what you expect. A set of stars in between the main sequence and the white dwarf sequence, and a big diffuse blob in the center faint end of the diagram. Now, this is all the stars. In addition to the measured values, Gaia Data Release 2 gives, as I said, the uncertainties of each measured value. But in addition, it gives a number of reliability parameters, a number of quality parameters on each measured source and each measured parameter. And these quality parameters have been simply ignored here in this diagram. Taking them into account, you can get a much cleaner and nicer diagram. This is an indication and an advice to every user of Gaia Data Release 2. Look also at the quality indicators and check whether these quality indicators can help you to get better science. How well this works is nicely shown in this Hertzsprung-Russell diagrams. In the middle, you see a much cleaner main sequence, a much cleaner white dwarf sequence, and you see that the space, the diffuse space between the two sequences and at the bottom center of the diagram has emptied very much. What has been done here is to look at the Chisquare Field of the catalog table, which tells you how well the individual observations, Gaia observations that created this set of parameters, parallax, proper motion for the star, did fit together compared to their expected scatter. Removing those that do not fit nicely, it's described in the paper how this was done here in detail, you see that a lot of the rubbish in the left diagram has disappeared. it is much cleaner now, and you can be much surer about the actual character and location in an Hertzsprung-Russell diagram of the remaining over 90%. Going to the right-hand diagram, another selection was done, now on photometric grounds, in addition to the astrometric selection that created the middle diagram. The philosophy here is Gaia measures magnitudes in 3 bands, in 3 different instruments, namely the broadband G magnitude, and then the red and the blue filter magnitudes. Now, for any given object, the red and the blue magnitudes, or the light fluxes in these 2 bands added together, should be similar to the broadband, which is just the sum of the spectral range of the 2. If not, you may expect that something with the photometry is bad, or maybe the star is complex, is a multiple, or has a nebula around it. So both the astrometry as well as the photometry are in doubt. The photometry is needed to place the star in this diagram, not just the parallax. So removing those that have unreasonably much flux in the blue band and in the red band compared to the flux in the sum of the 2, namely measured in the white band in the astrometric instrument, creates this much more cleaner diagram. Now you still have something in between the main sequence and the white dwarf sequence, but I can tell you most of these now will be binary stars between a main sequence star and a white dwarf. Astrophysically interesting objects. Also, if you look a bit more closely on the white dwarf sequence, you will see that it splits up in several very nice sequences, 3 sharp dark sequences, densely populated sequences, which correspond to chemical differences. These sequences, this branching of the white dwarf sequence has been predicted for a long time theoretically, but it has never been seen so nicely. Also, if you look a bit on top of the white dwarf sequence, you see a fainter, thinner one that is binary white dwarfs. And similarly so, you can see a binary sequence slightly above the main sequence at the right in the diagram. And these sequences are 0.5 to 0.7 magnitudes above the single star sequence, as you could expect. So there's a lot of wealth and beauty in these diagrams, which is marginally seen even in the raw diagram. It's displaying everything at the left in this graph, but it is much more nicely seen on the right. So that is the advice. Take the data, look at them, and look also at the quality indicators. Maybe you can get nicer science out of that. Another example is figure C4 of that paper. All sky maps showing the distribution of stars having measured parallaxes larger than 20 milliarcseconds. That is the all sky map of all stars formally, nominally, within 50 parsecs of the sun. Now, 50 parsecs is a tiny sphere around the sun, and the stars are distributed homogeneously in this sphere. That's clear from everything we know about the Milky Way. So they should be equally distributed on the sky, as seen from the sun. The left part of this diagram shows they clearly are not. You see the dense parts of the Milky Way clearly superposed, and you see a nice triangular patch at the bottom left of the diagram. So this cannot be true. It cannot be true that so many stars are concentrated within 50 parsecs along the Milky Way as seen from the sun and in this triangular patch. Again, these are all the stars with parallaxes larger than 20 milliarcseconds. Doing the same selection as before on the Hertzsprung-Russell diagram, namely taking into account not just the formal errors, but also the quality indicators, you get the middle diagram. This Milky Way band get very, very much fainter. The triangle at the bottom left has completely disappeared. So for most of the sky, we now have the expected homogeneous distribution within 50 parsecs around the sun. So you can say that except for this remaining Milky Way patch, all these stars are really within 50 parsecs of the sun, you will get a very nice solar neighborhood census from this. This was only the astrometric quality indicators. Now let's again add the photometric quality indicators. This gives you the right-hand diagram. Now all the disturbances have gone. There is a completely homogeneous distribution of these stars across the sky, except for one patch. Now, that is a real feature of the solar neighborhood. That is the Hyades cluster. So that means in this diagram, you exclusively have the real set of stars measured by Gaia really within 50 parsecs. This is just a second example of how intelligent and critical usage of the Gaia data can give you much improved scientific results.